So I'm just going to show you a quick overview of how you can use the real-time interface and then show and try to explain how we actually implemented it at a high level. So basically, VirtualCNC can do the simulation, and then using that simulation, VirtualCNC can implement it on a real machine that represents a simulated model. So there's basically 4 steps to actually go from simulation to implementation. The first one's pretty simple. Before you run the simulation, you just got to check this checkbox, real-time systems, and then you run the simulation as before. So you'll see the same results as you did before. Nothing's really changed. Then you click Run on Machine. Now, running on machine will open a new dialog box where first you click the Configure button. The Configure button opens this configuration parameters window, which sets up the parameters for the real-time build. So to convert the Simulink model to compiled version to run on the DSpace. Now, most of the settings that I have default for our system don't need to be changed, but you could set some parameters if your system is different or you want to change how the code is generated. So for us, we basically click OK. Then you simply click Build, and Build will start the compiler, and it'll take the Simulink model, convert it into C code, into an executable, and load it onto the DSpace. It'll also open the real-time interface then after it's completed building it. So you build it, and then after a little bit of time, this is the interface that opens. Now, this is the interface that you will use when you're trying to operate the machine and control it in real time. So you can see that there's a graph. There's 3 graphs. There's the X, Y, and Z axis. And then you can also toggle between X and A axis, between Y and B axis, and Z and C axis. If you have a 5-axis machine, you'd have some rotary drives there. So you can see all the parameters. And it'll look just the same with the same options. So I'm just going to explain the controls from one of these because they're all the same for the individual axes. So for the X-axis, there's this box which is the command voltage. And basically that tells you what the output voltage is of the DSpace, the DSP unit.
From computer to amplifier of the
right.
machine, of the drive. Okay.
So that's the voltage that your amplifier would be seeing for that motor. It's important to make sure that it's 0 when you start so that your machine doesn't jump. There's a saturation low and a saturation high, and that is a saturation voltage limit of the output of the DSpace. So if you want to test it initially and you don't want your drive, if something's unstable and you don't want it to go flying, you can set that low so that the drives will be limited in their torque, so that it'll move slower in initial testing. So the maximum output is 10 volts, so in this case it defaults to 1 for start. There's also an a maximum movement. The maximum movement is basically a software limit. So if you set it to, say, 10 millimeters, it means from your starting position, if it moves more than 10 millimeters in either the positive or negative direction, it'll shut off the power to that amp for safety. There's also, after you run a trajectory, it'll show it here, and if you want to look at it in higher detail and zoom in, you can do plot x-axis, and it'll show you the commanded position as well as the actual position and encoded position results, and you can zoom in and adjust that. There's also an encoder gain, which is taken from the simulation model, but if for some reason you had the incorrect value, you can adjust it here, though it's best if it was set correctly in the simulation model. There's also a jog axis button. So this allows you to move the axis without running a trajectory. So if you need to position it in the center or move it, you can enable the controller, and then by clicking this, either positive or negative, it'll move the axis, the increment specified here. So right now, if I would click the button, it would move it 1 millimeter. You could make this as large as you want. There's also this button, Invert X Gain. It inverts the gain input. So if when you do your simulation, that's not very important because it's assumed to be correct. But when you're running in the real-time machine, the input of your gain is very important for a stable system. So if it's wrong, you can adjust it by clicking that button. But you need to be very careful with that too, because if it's clicked while it's running, it would go unstable in a catastrophic manner. So that's the basic control of the basic input-output of each axis. Then the actual control of the machine is taken care of here on the right. So when you click Start, that enables the controller. It closes the loop of the controller, and the machine's now active. It's not going to start moving on a trajectory, but the controller's active, and if it's stable, everything is Stop is fairly explanatory. It just stops everything. Start trajectory will start the trajectory that you've programmed in your simulation to start running. By default, it's at 100%, so it'll run at the speed you specified. You can also pause the trajectory at any point, and it'll hold the position, and then you can either stop it or continue on from that position by clicking start again. This slider and percent here adjusts the feed rate. So you can adjust from 0 to 200%. So if you want to start your trajectory and run it slow, you can set it at a low percentage and run it slow.
Just feed override switch, basically.
That's right. There's also another safety here. It's called tracking error limit. So right now it's set to 1 millimeter here. And basically what that does is it monitors each axis. And if one of the axes input and encoder position varies by more than a millimeter, it shuts off the power going to that axis because it says something's gone wrong here, we're tracking too much, maybe something's unstable or you've hit something, so it shuts off the power to there. There's also a button here to save the results. So after you run a trajectory, you can save all the results. It saves it all in a file, the input, the time, and the outputs, and you can do that for further processing. Also, this allows you to do spindle control. So if you actually want to cut apart with it, if you input an AP file that has the spindle speeds, it'll get propagated through and it'll come here. And so there's only a few controls. Basically, you can do spindle override. So you can adjust it, either give it an increase in RPM or an increase in percent of the speed. And it tells you the commanded RPM and the commanded voltage going to the machine. That's basically the overview of our user interface. So as you saw, VirtualCNC basically creates a Simulink diagram with the plant model. So when you go to run RealTime, VirtualCNC does two things. One, it takes the plant model and replaces it with the DSpace real plant. So it replaces it with the DSpace encoder inputs and digital to the actual system, the real system. So it basically replaces the real system, and then Simulink RealTime Workshop compiles a C code which gets loaded onto the DSpace computer. At the same time, VirtualCNC opens the GUI, which then connects to the real-time computer and streams information to and from it, and that's what you see as user interface. It updates the values and sends commands to it. DSpace on the hardware side connects to the real machine, the drives, via the encoders and the outputs to the amps and whatever else, and talks to it that way. So that's basically how we implemented it using the DSpace real-time system.
Let's say this is x-axis, there is another one y-axis, z-axis, and so on. A reference trajectory means position command to each drive. So these position commands are stored in a file as a function of time. Because if we, for example, send 2 micron per millisecond, the command velocity is 2 micron per millisecond. But position command is 2 micron. In the second millisecond, we can say 4 micron. Now we are accelerating the machine. So by adjusting the time interval, we can adjust the velocity, acceleration, and jerk. So these commands are stored in a file by VirtualCNC. When you want to test them in real time, the real-time system reads these line by line and sends commands to the individual drives in real time. Then DSpace has a real-time clock. Let's say you say 2 milliseconds. It will wait 2 milliseconds before sending the command to individual drives. Okay. And the real CNC, of course, trajectory generator and this, they work simultaneously in parallel. And in fact, trajectory generator usually works a few hundred blocks ahead, like a look ahead. That we will also implement here, because we need to look ahead to see the error, incoming error along the path, and compensate the error early on. You can't compensate once it happens, once you cut the path. What we need enough computer time to calculate and correct the path. And buffer time before we send them to FID drives. Once you send the FID drives, there's nothing you can do except design a good controller here, design a good controller which does its best. But its best may not be good enough for you. Yes, this is a very important question. We can predict the cycle time for our CNC because we build it ourselves. We know everything inside. But industry, such as Pratt & Whitney and Boeing, they are demanding from us to predict the cycle time of Fanuc and Siemens. It is difficult. The reason is we don't know what they are doing inside the CNC. We will identify servo dynamics. That's one topic. We are doing these things, but we have to do this on a real machine, on a commercial machine, with limited access to CNC. We have using servo guide, right? Servo. We have focus and servo guide. With the servo guide, Fanuc gives you frequency response function of the velocity loop without the controller, and you can read the controller from the panel. Then we can build controller, but they do more than that. We don't know what they are doing in the trajectory generation. They never publish, they never tell you. The cycle time is determined by, total cycle time is totally determined by how whether you use this type of trajectory generation or this type of, or do they corner smoothing. We don't know what they are doing inside. This is the biggest challenge, because that will not the control of each drive, because machine will be controlled at every 1 millisecond. The tracking error, delay between input and output will be always in milliseconds, not more. But the command, for example, we are telling, the operator tells the machine to go around the circle 100 meters per second. We know it's impossible. But CNC will accept it and disregard it. Inside the CNC, it will pass through this trajectory generation, and the CNC will say, hey, I can't do this. I don't have the computer time, and I don't have the torque on the drives to accelerate the machine so fast. So it will use some default values inside. We have access to some of these default values because CNC manual tells us from the parameter table. But we got some help from Moriseki, CNC guys, to find out where they store those parameters. Okay? But let's say corner smoothing. If you don't smooth, it has to go, stop, and accelerate again. Time is different. If it doesn't stop at all, it has to keep going. It can never go around the 90-degree corner without violating. What they do, like we do, they put small micro spline in the corner. So the machine never stops, and the transition from one direction to another, velocity transitions become smooth. We don't know how they are doing it. They never tell. From that point of view, it is very difficult to estimate cycle time of a commercial machine, although everyone is asking us to do it. Who can do this best? CNC builder himself, because they know what they did, they put inside. But this is a subject for us. We kept visiting this idea because our research sponsors want that from us. Why do they want them? They are looking at the moment 10, 15 different machines. Without testing every one of them, they want to load the NC program on the virtual model of that machine and see which one is able to cut the part faster before they travel and do lots of tests and waste their time. Then they can narrow the machine to 2, 3. It will save them lots of time and money. That's why they want this. But it is not easy because we don't know what they are doing inside the computer.